Welcome to 25th KES conference. Our topic is project-based learning within e-health, bioengineering, and biomedical engineering application area.
It's my pleasure to introduce the authors of this topic. They are Jeffrey Young, Maria Spikakova, Milan Simic. They all come from RMIT University in Melbourne, Australia. The Melbourne Bundoora campus is 18 kilometers northeast of Melbourne city centre, a relaxing environment surrounded by open space and native parkland. The campus houses many RMIT engineering, health, and medical science and education programs. The key facilities include multi-purpose built health and medical science laboratory, the dedicated engineering campus.
We would like to introduce two project results in e-health, bioengineering, biomedical engineering, and the related application area. The two projects was conducted in School of Engineering and School of Computer Technologies.
The projects in this topic either come from industry or reflect real industrial problems. The university lab are state-of-art, such as RMIT's Centre for Additive Manufacturing Incorporated in STEM College. The Virtual Experience Laboratory, a multidisciplinary virtual laboratory connecting vision stations and automation facilities. These projects give students a teamwork experience. Students can learn how to organize their work. Actual goal is to make the learning collaboratively. The first project is gate monitoring system. This project is cooperative with a multi-university gate laboratory and hospital, also with a medical instrument developer company. Gate modification include foot projection angle modification, can help people release from lower limb disease and recovery participant walking ability. More than 10% Australians are reported have walking problems, from toddlers to aged people, from flat feet to osteoarthritis. Their personal gait modification strategies or orthotics products must be made after their gait information being examined by either traditional gait laboratory or wearable sensor monitoring system. The gait modification plays an important role in orthotics, prosthetics product, bipod robot, and exoskeleton application. The most important parameters of gait are foot projection angle, foot flight phase, step width, step length. The foot projection angle is defined as the degree of external rotation of the foot with respect to the direction of progression. The foot progression angle is measured at foot flight phase stance only. The accuracy of foot flight phase detection is critical for foot projection angle measurement. The foot flat face has an important function since body weight is transferred to the lead leg at this point and must absorb this weight while maintaining forward momentum. The step width, step length, and step speed, all these parameters calculation is based on this foot flat face stage. The downward facing camera is mounted on the participant's upper body or torso via a harness shown in the picture. The camera does not have to be perpendicular to the walking plan or any reference. Any people can wear it on without calibration or technician support. Here is the logical sample code. Shows the project program how they work in the video stream to detect the foot angle and the other gate parameters in the stream. In the nature walking speed, there are 3 stages within each foot flat face. The third stage has less impact from the ground, allows the speed, better view catchment, and better image quality. Therefore, we measure all the gate parameters mostly in this stage. In the video stream, the photos were filmed in 30 Hz frequency. In the 2 successive images, the image features were matched and compared. Therefore, we can calculate the displacement of the features in 2 successive images. Based on that, we can calculate the speed of the moving object in the video. Now we can summarize the foot projection angle algorithm as shown in the flowchart. In this page, there were 4 groups of data and the image were shown in the sequence of the frame index in the video. From the left top corner, we can see the frame index is 944. This image was shot at the early stage of the foot flat face. At this stage, we can see the body trunk 3 angle is 12.67 and the foot speed is 35 centimeters per second. This means the foot is still moving, so we don't accept the data on this stage. On the left bottom corner, we can see the foot speed is dropping by 5 centimeters per second. Actually, at this stage, the foot is almost flatly on the stage because the ground force impact to the body and the calculating errors, they told us the foot speed is still moving. So as soon as we set up the threshold to eliminate the calculating error or the camera impact parameters, we accept this one as foot flat face beginning. At the right top corner, we can see the foot speed almost dropped to 0. At this stage, the foot variation angle is 19.4. At the right bottom corner, we can see the foot speed is absolutely 0. This means at this stage, calculation is very stable because no ground response force apply on the body, and this time the body's speed is slow. You can see the camera position right on the top of the supporting foot. And this is the best stage to take the picture and take the calculation of all the gate parameters. So in each stage, we detect the foot flight stage from the frame 944 to the frame 1000, and we collect all of the image and the data. And after analysis this data, we take the best result at the foot speed equal to 0. Normally, at each step, we can get more than 10 pair of images with the foot speed calculate equal to 0 or minus plus 5. So we get the average of the foot speed and the other parameter matters in the average value to accurate the result. In the body-worn camera system, ground and foot moves respect to the camera with different speed. When both foot speed and ground speed are same, this means foot are flatly on the ground. This means its foot at this stage. So in this picture, we can see when the supporting foot is foot speed and ground speed are detect and calculate. The difference or the offset of two speed is shown in the purple color. When the purple line is getting to 0, as shown in the stage 4 and the point D, we can find the speed of foot and the ground are same. Also at this stage, their speed is lowest. So we pick up the gate parameters from this point. This is the algorithm. We detect the foot flight phase and measure the foot position angle. During the normal walking speed at point D, there are 4 or 5 pairs foot progression angle were measured. Their average value will be taken as the foot progression angle of this step.
Real-time data was present in both digital and graphic interface. They show the gate parameters measurement in real time while the video is taking, and at the same time the data was analysis. A team of 6 students was working on CAN appeal project. This chart presents some example of the interface of the clinical trial application. The system supports several types of users, from doctors and academic researchers to the patients and caretakers, as well as system administrators and the clinical trial coordinators. The application elaborated within the capstone project contributes to the CAN appeal platform creation. The core idea of the platform is to use the collected data for the efficiency analysis of cannabinoid treatment of various disorders to provide an evidence-based assistance for doctors, researchers, and the industry to identify the right cannabinoid profile for various conditions. For the data analytics we utilize Apache NiFi along with the Vertica and MicroStrategy platform. The core analysis was performed using RStudio, an open source software for R language, and the library association rules on the basis of the a priori algorithm. For data mining, the framework applies the VECA a priori association as analytic algorithm. The chart illustrates the data collection and processing within a elaborated framework. The data was collected from Apache NiFi and moved within streaming processing engines. HEAD-OP cluster and OLAP online analytic processing engine. We applied the framework on a number of case studies to analyze correlations along medicine consumption and weather conditions. Experimenters will conduct and select a data set for specified medicine generics ingredient description code, where we have focused on the data on the drug acting against the allergic, autoimmune, and transplant-related disease, cholesterol, hepatitis, and asthma. In this paper, we have presented an overall work integrated learning project conducted at RMIT University as part of the learning and teaching activities in the STM College, with the focus on e-health, bioengineering, biomedical engineering, and related application area. We have shown how real-life projects are embedded into the curriculum and present a number of recent projects conducted by our teams in collaboration with industry partners, other academic institutes, and medical practitioners.
Here is some reference we used in these presentations. Thanks for your watching, and we are welcome to answer all your questions. Thank you.